Okay, so it's a pleasure to have Oscar again giving his second talk on geometry of vortices on Riemann surfaces.
Thank you, Nuno, and thank you everyone for being here. Last time I introduced the abelian vortex equation on a compact Riemann surface that has been mentioned by other speakers. And I was explaining a relation with the basic equation of Hermitian-Einstein or Hermitian-Yang-Mills, in fact, as a way of proving existence theorem of the vortex equations. Let me remind you that this, so just to recall that the setup for the Hermitian-Yang-Mills equation is a compact Kähler manifold of any dimension. For us, will be complex dimension 2, and we normalize the volume conveniently, and then we have a holomorphic vector bundle over the complex manifold, and the Hermitian-Yang-Mills equation I prefer to think now as an equation for a Hermitian metric on the vector bundles. I'm fixing a holomorphic vector bundle and I look for a metric. You can view this as we have been looking at the vortex equations, like you fix some Hermitian vector, C infinity vector bundle, and you are looking for a holomorphic, you're looking for a connection that satisfies this. So these are equivalent point of view. This is a relativistic, idea here. You can go back and forth. And so we prefer to fix the holomorphic structures, which is like fixing a connection that defines a Dolbeault integral Dolbeault operator, so a holomorphic structure. And so then we are looking for a Hermitian metric on the bundle, and recall all these terms that we have the curvature of the unique connection compatible with the metric that is unitary and also compatible with holomorphic structure. And the curvature is a two form with values in the skew Hermitian endomorphisms. And once we contract with the Kähler form is just a Hermitian endomorphism, a section of this bundle. And we just ask that this be, in fact, mu times the identity of the bundle, where, in fact, mu is determined by the topology. Mu, by just taking traces here, you realize that this scalar here is, in fact, what we call the slope of the vector bundle, which is the degree defined in terms of the Kähler form divided by the rank. Yeah, so there is no flexibility there. There's no, like in the vortex equations, we have a parameter. Here, this thing is fixed by the topology. So this is the Hermitian-Yang-Mills equation, and just recalling you the Hitching-Kobayashi correspondence, which relates the existence of that equation to the algebraic geometric condition of a stability. And so a stability of vector bundles on Riemann surface was introduced by Mumford in the early 60s. And this was generalized by Takemoto in higher dimensions in this way, that you say that a vector bundle is stable if for every coherent subsheaf, the slope of the subsheaf is smaller than the slope of the bundle. And remember that coherent subsheaves are really outside of something of certain codimension, are really vector bundles. And so it makes sense to define the degree and the rank. And in fact, if M is a complex surface, we can think of E prime itself as a vector bundle, not as a subbundle of E, but as a vector bundle, right? And so the condition, another relevant condition then is that of polystability, which is that bundles are X sum of vector bundles stable, all of them of the same slope. And the theorem, the Donaldson-Uhlenbeck-Yau theorem, states that the existence of solutions to the Yang-Mills equation on the vector bundle is equivalent to E being polystable, and in particular, if the solution is irreducible, then the bundle is stable. Okay, so this is the Donaldson-Uhlenbeck-Yau theorem. And so let's come back to the vortex equation, but I want to look now at the vortex equation, not as I presented it originally as an equation for a connection and a section, but I am going to take this other point of view in which I fix a holomorphic line bundle, and I fix a holomorphic section, and I'm looking for a metric, similar kind of thing, right? I'm looking for a Hermitian metric, and the shape of the equation is the same. Of course, I don't have now the other equation. That is, it is clear, I mean, I have it because the fact that phi is holomorphic means that d bar of phi is actually 0, right? But it is implicit in here, right? So, and so this is the vortex equation from the point of view of looking for a Hermitian, for a metric on the line bundle. You will excuse me. So now, here's the key thing, that the key thing that will allow us to apply the Hitchin-Kobayashi correspondence is the fact, a very basic fact, that to align a pair consisting of a holomorphic line bundle and a section, you can associate in a very simple way a rank 2 vector bundle, holomorphic vector bundle, over the product of X cross P1. This is going to be my complex surface. It's a Riemann surface cross P1, right, CP1. And that bundle is specifically given as an extension of the pullback of the line bundle on X to the product by the pullback of the line bundle, the line bundle of degree 2 on P1, right? And the tangent bundle of P1. And why do I have this correspondence? Why is it true that pairs like this are in correspondence, I claim, with vector bundles like this? This is something very simple. You have studied maybe how you parameterize extensions of a holomorphic bundle by another, right? And extensions, in fact, this applies also to coherent sheaves and so on. There's a first cohomology group that parameterizes that, and you take the bundle in the kernel, H1 of the bundle in the kernel tensor by the dual of the bundle in the image. And this is the O-1. And so now you have simply the Kenneth formula that allows you to express the first cohomology on X cross P1 in terms of cohomology on X and P1 of the corresponding line bundles. And I have already canceled the H0 of P1 with values in O-2, because having degree -2, there are no holomorphic sections. And so the H0 with values in O-2 doesn't appear. So I only have this. And now just this H1 here by third duality is just functions, holomorphic functions on P1, and those are the constants. So in other words, extensions like the ones that I am describing are precisely parameterized by holomorphic sections. If you think in terms of how you represent a, this is also a useful point of view if you want, how you represent the Dolbeau operator of this in terms of Dolbeau operator of this holomorphic and this one, there is like a second fundamental form that is in the off-diagonal sort of, say, you sort of, if you want to express the Dolbeau operator, there is one here, then the other here, and then there is something here, which is like second fundamental form, something. And the point is that phi codifies, you know, the second fundamental form. Phi is incorporated there, right? You would say, well, but the second fundamental form is a 1-0 form, it's a 0-1 form. Well, the 0-1 part comes from the CP1, right? But so that is how you can see this very easily. Anyway, so we have this holomorphic bundle, but this holomorphic bundle is not just a holomorphic bundle on S cross P1, it's an equivariant vector bundle. It's equivariant. You see, P1 is this symmetric space, SU2 mod U1, and is an equivariant in the action of SU2. Actually, the bundle itself is equivariant under the action of SL2C. In fact, P1 is also P1 is also the quotient of SL2C mod this parabolic subgroup like here, you know, this in here, right? And so this vector bundle is invariant under the action of SU2 and the action of SL2C, where I am considering on X cross P1 the trivial action on X and the natural action on P1. I care about SU2 because I'm going to solve about metrics. And so the metric I want to be really SU2 equivariant, right? And so, but okay, so I do have this equivariant vector bundle. And now I claim that on X cross P1, I do have an SU1, SU2 invariant Kähler metric, which is just the pullback of a Kähler metric that I have chosen on the Riemann surface on the part on X. And then I have the pullback of the Frobenius study that I normalize. There are several kinds of ways of normalizing. I could put the tau here, and but one way is this. The 4 is not so important. And so you see the vortex parameter tau is now incorporated in the Kähler metric that I have here, right? And I take tau bigger than 0, otherwise this is not a metric, definite metric. And so here is the argument of the proof. I mean, it's a simple computation to show, really computation is easy, that the solution to the vortex equation on X is equivalent to having an SU2 invariant solution to the Hermitian-Yang-Mills with respect to that metric. Really easy computation. This part is also easy. It's easy, sometimes, oh, this is some kind of stability condition. It is a stability condition. And in fact, it is equivalent to the stability of the vector bundle with respect to the Kähler form there. The difficult part in the proof is given by this theorem here, the Donaldson-Uhlenbeck-Yau. The analysis is hidden there. Right? So this is really like killing a fly with a canyon, right? But this is a very powerful thing, as we will see, because in different situations, they will provide more substantial. But this is the way that one way of proving the existence of solutions, and also having some understanding of that condition, really in terms of some stability. And this is why I claim, vortices on X are really SU2 dimensional reduction of instantons on X cross P1. And this idea was not very original. I mean, this was really already going to Witten, who showed that, in fact, vortices on the hyperbolic plane are invariant instantons on R4 under some rotations under one fixed line. And also Taubes, in his beautiful papers on the vortex equations, didn't use this to prove anything, but he commented that indeed the vortex equations on R2 are dimensional reductions of instantons on R2 cross S2, invariant under rotations. All I did was to put this in a more algebraic geometric context of vector bundles. And that will prove, actually, as you will see, very fruitful, I think. And you see, at the time when Witten was looking for that, and people were obsessed by looking, finding solutions to the instanton equations. And this was actually about around the same time as the ADHM construction, the Differentiation-Manin description of construction of instantons on the sphere, on S4, and using twistor theory, right? And so one of the reasons why physicists like to do dimensional reduction is because it is easier to find solutions with symmetry. And in fact, in the case of Witten, as already Martin mentioned, on the hyperbolic plane, in fact, the solutions to the vortex equation can be very explicit in terms of Liouville equations and so on. Anyway, so this was the inspiration for this process. And so I want to go now, I want to get non-abelian. So this was the abelian vortex equations. And so where historically, if you want, several non-abelian directions. And so the line bundle L can be replaced by a higher rank vector bundle, holomorphic vector bundle. And now we have a holomorphic vector bundle V and a section phi. And there is, Bradlow introduced this equation, which, like the abelian case, these equations are dictated by symplectic geometry. In the same way as the abelian vortex equations appear as moment map equations, the same happens here. And so in this situation, the norm of the Higgs field is replaced by taking the endomorphism that one obtains by tensoring phi with the adjoint of phi with respect to the metric. So this is an endomorphism of the bundle, skew Hermitian, that or not skew Hermitian, excuse me. It's just an endomorphism, and you can it's Hermitian actually, and you can confront it to this term in the curvature, and you ask this to be tau times the identity. So that is the equation that Steve Bradlow considered, and so then I also played the game of this dimensional reduction point of view by realizing that, in fact, in the same way that I put a line bundle here, I could put a vector bundle and still have the same correspondence. Now, the Bradlow proof and existence theorem then was more substantial because the existence of solutions of this, some kind of Hitchin-Kobayashi correspondence, was equivalent to the polystability, some notion of polystability of the pair. So I was working on this when I saw this condition, and I found that condition very difficult to understand. And in fact, the way for me to understand it was, again, to interpret it as a true stability condition on the vector bundle with respect to a Kähler form, which essentially, is some term, as before, right? It's the pullback of the Kähler form on X and the Frobenius 2D metric multiplied by some positive thing depending on tau, right? Very explicit. I just was lazy to write what it is. And so instead of telling you about this stability condition and beautiful story about how this different moduli spaces change and so on, I want to go to a slightly more general setup, and which in a sense will explain the thing, but I'm just observing here that this point of view of dimensional reduction is telling you that the moduli space of rank n vortices, like the rank 1 vortices, do live inside somehow of the moduli space of rank n+1 stable bundles on X cross P1. And they live in some fixed point subvariety of that moduli space. In fact, that provides a construction of the moduli space, right? But as I say, instead of telling you the story of what is the stability condition here, I will go to this slightly more general condition, more general setup of what we call triples. So these are non-abelian vortices and triples. And so the triples here being, in fact, two vector bundles and a homomorphism of the vector bundle E2 to E1, you will understand, of course, the order. And the reason is that, again, the fact is that we can still construct, there was no reason for this to be a line bundle. We could put a vector bundle. There is no reason why we shouldn't put a vector bundle here coming from X, where in the original situation, there was just the trivial line bundle, the pullback of the trivial, right? So you can, there is a one-to-one correspondence between triples like this over X. X is still a Riemann surface. All this can be done on a compact Kähler manifold, but we care in these lectures only on Riemann surfaces. And so then the fact is that extensions like this, again, by applying Kenneth formula and their duality and so on, are parameterized by Hom from E2 to E1. In Hom, this phi can be incorporated in the second fundamental form. And so now the vortex equations, which appear as, of course, moment maps are, and we look at them again as looking for Hermitian metrics, is we're looking for a Hermitian metric H1 on E1 and H2 on E2, and the equations are like this, right? And now you realize that, okay, this is, if you take phi adjoint, this is an endomorphism of E1, so it makes sense to ask for this. And then, the symplectic form that you have in the setup dictates that this has to be a minus. And this is the other piece that you can confront to this. And now here you see two parameters, two real parameters, except that if you now take the trace of this and you take the trace of this and add them, these two terms cancel. The traces are the same. Right? I mean, they have this a different sign. That's the point. They cancel, and by Chen-Wei theory, you can link the two parameters to the degrees of the Chen classes of E1 and E2 by this, and the ranks, right, by this simple expression. So you really have just one parameter, right? Which is, you may choose tau 1, you may choose tau 2. We'll see that we won't choose either one, but in fact, the combination of both will come naturally. And again, phi star is the adjoint of phi with respect to the two Hermitian metrics. So notice that the coupling of the term, the Higgs term to the curvature depends on the metrics. H1 and H2 intervene here and here. Okay, just not to make the notation so heavy. All right, so the thing is, now in this setup, it's a little bit easier to express. Question. I will comment on that in a second. Yes, the answer is yes, but I will. And right, so having this setup of triples as opposed, I mean, of course, the Bradlow pairs is a particular case of a triple in which E2 is just a trivial line bundle, right? It's going from O to the bundle, right? But it's a slightly, the role of E1 and E2 is not symmetric. And so when you put it in this symmetric way, it's quite nice to express stability conditions. This is an abelian category. And so you can express things very nicely. So first of all, a homomorphism between two triples is just nothing but just, this kind of commutative diagram. And you can make sense of what a subtriple of T is by just requiring that this sheaf homomorphisms, I say sheaf homomorphisms because I'm not requiring this to be subbundles. But I mean, of course, on a Riemann surface, they are bundles, right? But the inclusion may not be a bundle inclusion, right? There may be some torsion in the quotient. And so these are injective, right? So this is a subtriple. And now, it turns out that you can define very naturally, if I give you a real parameter alpha, a slope of the triple that depends on that parameter. And the slope is defined as follows. It's just the slope of the usual slope of the direct sum. So the degree of this divided by the rank. And then there is this term depending on alpha, right? And again, we are dividing, like in the slope, we are dividing by this. But here we are singling out rank of E2. Well, this is how we define the slope. And so alpha slope, depending on a real parameter, right? And this is prepared to define, of course, a natural notion of a stability, alpha stability of the triple by saying that if this alpha slope of any subtriple is a smaller, I mean, any non-trivial subtriple, and non-trivial should be obvious, right? That they are not all zero or the same triple or something. And so for any proper subtriple, the alpha slope of T prime has to be smaller than the alpha slope of T. And generally, you define semi-stability by relaxing the strict inequality to just weak inequality. And alpha polystable being that the triple is direct sum of triples, all of them with the same alpha slope. And it should be obvious what I mean by direct sum of triples, right? So the bundles in E1 add up, the bundles in E2 add up, and the morphisms go, that's what I mean. And so this is a rather, it maybe looks funny condition, but it is actually exactly the condition. So I introduced the equations, in 91 or something for triples, but I joined forces with Steve Bradlow, and so we prove the existence theorem that says that if tau 1 and tau 2, these two parameters that we have in the, we called them originally coupled vortex equations, but just say vortex equations, satisfy necessarily this, remember, they have to be linked like this. But now you take alpha, the parameter somehow is the difference of these two real parameters, right? Then the existence of solutions in the triple, this Hermitian metric satisfying the vortex equations is equivalent to the alpha polystability of the triple, where alpha is exactly, as I said, there is just one real parameter, and that which is to be alpha, which is what appears naturally in the stability condition. And again, the strategy to prove this is very similar to what I presented in the abelian case. You have to do two things. First, you show that the alpha stability and alpha polystability of the triple is exactly equivalent to the polystability or stability of the associated vector bundle on X cross P1. You see, because of this correspondence, actually, you can see why triples behave like is an abelian category. You know, they are like vector bundles, right? I mean, precise statement is that, right? And again, now in the Kähler form, you incorporate this parameter. Actually, it can be precise statement is that the Kähler form that you take on X cross P1 is omega X multiplied by alpha positive plus the Fubini, the pullback of the Fubini's 2D metric. And that's one thing you have to do. You have to relate the stability condition of the triple that we have defined to the stability of the vector bundle. And then you have to show that indeed the vortex, the solution to the vortex equations is related to a solution of the Hermitian-Yang-Mills equation. And because you're looking for a solution which is invariant under SU2, and the vector bundle is what it is, you know, the vector bundle is really this thing, it boils down to just having a metric on E1 and a metric on E2, and it's just immediate. It's a computation. So, I mean, very much the same that was done in the line bundle case. Okay. So this perspective, again, is telling us that the moduli space of this triples, in particular, this gave an understanding of the Bradlow stability condition in a more sort of uniform way. And the original condition was a bit strange, but this is somehow clearer. Okay, so let's talk a little bit about the moduli spaces of the alpha polystable triples. And just I want to, this will be the moduli spaces that will be isomorphic to the moduli space of vortices in that setup. And we fix the type N1 and N2 and D1 and D2. These are the ranks and the degrees, right? And so this is a complex analytic variety, and you can see it's projective when alpha is rational. And in fact, as I said, the dimensional reduction perspective goes a construction of the moduli space by realizing this as a subvariety of the moduli space of stable bundles that is constructed. It has been constructed by Gieseker and others. But actually, Alexander Schmidt gave a direct GAT construction of this moduli space as, you know, like you construct the moduli space of vector bundles using geometric invariant theory. So that's very satisfactory. That shows that it's a projective variety and so on. And now, here is, you know, I want to single out the substantial differences with the case of the abelian case, the line bundle case. And so to do this, let's just call MI the slopes of, you know, E1 and E2 that we fix like this. This will be fixed, mu1 and mu2. And I define this alpha sub little m like this, the difference of mu1 minus mu2. And then I define this alpha m to be this number here, when n1 is different than n2. Otherwise, it doesn't make sense. Actually, if, well, let's put it this way. If n1 is equal to n2, I declare alpha m to be infinity, right? And so the statement is that a necessary condition for this moduli space to be non-empty is exactly that the parameter alpha be in this interval between this smaller value, alpha sub m, and this maximal value here, if n1 is different than n2. And in any case, alpha has to be positive, I mean non-negative, right? And in the case where n1 is equals n2, I don't have a bound, an upper bound, but I do still have this lower bound. So remember that this was actually also asked in the when we were describing this, the abelian situation. Well, there we have the parameter tau, and remember we have d to be the degree of the line bundle, and the requirement was that tau had to be bigger than this or equal, right? So tau was living here, right? So it could be any value, and the moduli space was always the same, and it was a symmetric product. It was always the same as an algebraic variety, but of course the metric would depend on tau, but there was no changes, right? And there was no, I want to emphasize, even though this is, you know, this is like the alpha m in the story, and then there was nothing, you know, there was no limit, there was no bound on tau. So in particular, the volume of the symmetric of the moduli space can be, you know, as big as you want, right? This is not the situation here. In particular, when n1 is different than n2, it's actually quite the situation when n1 equals n2. This is like the abelian case. Because in the abelian case, I mean, there's only one line bundle. Well, there are really two, you know, it's like O to L, right? So a section is going from the structure sheaf to L. So really it feels more in this kind of setup. Yeah? So this is one feature. There is the parameter is a smaller, is a lower bound, and when n1 is different than n2, there is an upper bound. Otherwise, there is no upper bound. That's one feature. Now, other feature is that, in fact, now there are in this, say, okay, we have this alpha m here, and then infinity. There are a number of what we call critical values, where potentially you can have a subtriple satisfying the strictly semi-stability condition, that the slope of the subtriple equals the alpha slope of the triple. And somehow you want to, how can I put it? You want to single out those values because outside of those values, everybody is stable, not semi-stable. And that is kind of nice, right? So this is a simple computation. Notice that this is the potential alpha slope of a subtriple. This is the alpha slope of the given triple, right? And you say, okay, when are these equal? And so they are equal when alpha is like this. And you say, okay, those I will call critical values, right? And the point is that, well, there are some conditions here that we say that, yeah, the alpha is critical if it is actually one of those values, right? It's like this, with these conditions. Otherwise, we say that is generic, not critical. And the point is, these critical values, obviously, as you know, you can see, form a discrete subset of the semi-interval here from this to infinity, right? It's a discrete subset. But in fact, in the case where we have an upper bound, right? When we have an upper bound, that is when n1 is different than n2, the number of critical values is finite and lies exactly in the interval. So in the situation where we have an upper bound, there is just a finite number of critical values. One or two, something. Critical, some finite number. And so this is the this is a kind of situation that is, so the important thing is the stability criteria for two values of alpha that lie, excuse me. For two values of alpha that lie in the same interval between two consecutive critical values, the moduli spaces are the same. They are isomorphic. Again, if you care about the Kähler metric that is inherited here by the Kähler reduction and so on, the metric is different, but as varieties, they are isomorphic. The moduli spaces are isomorphic. So if you think about it, you realize that morally, okay, let's forget about the critical values for a moment, but for this non-critical values, there is just a finite number of moduli spaces that you care about. A finite number of projective varieties that are involved in the game, right? Now, there is a way of actually somehow imposing some coprimality condition so that you get rid of semi-stability. And so if you impose these conditions that sometimes, happen to be there in some particular applications of this, then the alpha semi-stability is equivalent to alpha stability. There is no equality ever. And so the moduli spaces are smooth projective varieties, right? And so you can actually, and so now the story is somehow, how do you study these different moduli spaces, right? And I want to just convey the idea that is, that first of all, that it's very easy to identify what is the moduli space when alpha is exactly the alpha m in the bound, this alpha m. And this is very similar to what was described in the case of line bundles. I think Nuno mentioned this at the beginning, that if you take this value of alpha, you're forcing this is the same phi as this, forcing phi to be 0. And so then the polystability of the triple is nothing but just phi 0, and this vector bundle has been polystable. And why do I say that the vortex interpretation shows this? Because when you go to the vortex equations, the terms in phi are 0, and you are simply saying that you have a projectively flat connection on one bundle and projectively flat connection on the other. And by the Narasimhan-Seshadri theorem, this actually corresponds to polystable vector bundles. So in other words, the moduli space is the product of the moduli space of vector bundles for rank 1, degree 1, and rank 2 and degree 2. Very easy. This is the analog of this dissolving limit, right? No, you call dissolving limit, where you got the Jacobian, right? You got basically a component of the Picard group, because you just have line bundles, right? Here you have 2 bundles and you get 2 vector bundles. Now, a more sort of substantial thing is, let's try to investigate what happens as you progress and you increase this parameter alpha. It's a very beautiful story, I think. I mean, I found very nice that as you progress and you make alpha bigger, somehow the triple behaves better and better. Well, let me tell you what do I mean. And let me tell you in the case actually where we do in fact have this upper bound, that is the ranks are different, right? So we have, sorry, we have E2 and E1, and this is phi. And what happens is as you make the alpha bigger, stability forces, first, one thing is that this becomes an injection. So after alpha big enough. And then you take the quotient, say the quotient is F, right? And so in principle, because this is just an inclusion of sheaves, F is something that we have torsion, the vector bundle and the torsion part. But as you make alpha bigger enough, is actually torsion disappears. And so it becomes a vector bundle. And so, can describe, and moreover, as you make alpha, and you can actually determine those values of alpha for which this phenomena happened. And when alpha is big enough, in fact, these guys here become semi-stable bundles, right? So basically, you realize that you can describe your moduli space for alpha sufficiently large, right, in terms of, again, moduli space of vector bundles and some extra data. And the extra data is actually given by extensions, by extensions of this, this becomes an extension of this by this. And so how do you describe extensions again? By some H1, right? And you can show actually that, okay, this H1 may be jumping, but it doesn't jump. And so here is what you obtain by, okay, let me just say this. Let's take alpha C to be the largest critical value before alpha M. So you have all these critical values, and so you just take the last one, right? So this is, I won't call it this alpha C, but this actually, will be alpha C. And so I'm interested in the moduli space in this, any alpha inside this open interval, right? And you can describe explicitly that I call it ML, like M large, right? And so this is, you can, by the arguments that I just mentioned, show that at least, okay, this means the stable. So you don't count the strictly polystable. So it's smooth of a given dimension. You can compute the dimension. In fact, the dimensions of all these things for alpha generic are always the same. But the point is that that moduli space is a Pn fibration over the moduli space of stable bundles. This corresponds to this E2, and this corresponds to this Fs, where I said that you have here like stable bundles. And then this projective thing is having to do with the extensions and the fact that there is no jumping. The stability of the triple tells you that there is, once you fix E1 and E2, if you vary them, there is no jumping, there is a vanishing result in some H0. And so therefore, you do get this projective fibration over the product, right? And you can determine actually what is the dimension of this projective space. In particular, and this is something, so far, I mean, we're talking about these moduli spaces, and we don't know whether they are empty or not. Certainly the one for alpha M, because the product of moduli space of stable bundles, we know non-empty, fine. But what about the others? So we don't know, right? And so here is the argument. So this shows that this is actually non-empty and actually is irreducible, right? So this is irreducible. In fact, you know exactly the structure of this one. And then if you, again, you have some coprimality conditions, then you can actually say that, that is non-empty and irreducible. And in particular, ML and the entire moduli space, now counting the strictly polystable, is also irreducible and then birationally equivalent to this. So you have a birational description of this. And this now is something that you can start with to try to investigate what happens for other values of alpha. This kind of game was first performed by Michael Thaddeus in the rank 2 situation. Question?
Birationality without having the isomorphism?
Yeah, no, indeed. In fact, this is what I will say now, that you start with this guy, which is the moduli space for this value, right? And now you typically are interested, for some reason that I will explain in a few minutes, in some value which is here, right? Some particular value. And so you're not necessarily lucky and know what the moduli space for this value, and you have to do this wall crossing, and this is the whole game. So in this paper with Steve Bradlow and Peter Gotten, we investigated the wall crossings, right, to actually realize that up to a certain value of alpha, as you move, now you progress to the left, right, all the moduli spaces are birationally equivalent. So what you remove and so on has large codimension. Okay, so that provides examples of what you're asking. The moduli space is not that, but it is birationally equivalent to that. My statement about the last one, I start with that one, and then I have to study what happens as I cross these walls, right? And what I'm saying is that I can study what happens at what are the changes that take place, or at least what is the codimension of the things that I have to add and remove. I can have bounds on what is the subvarieties that I have to add and remove, right? They can be described. And the fact that this is an abelian category is very important, because there you can study, you have all the Jordan-Helder filtrations to evaluate when something is semi-stable but not stable, right? And you can parameterize what are the bad guys, right? And so on, and you can study, it's not the detailed study that Michael Thaddeus did in the rank 2 case, where you can exactly say what are the birational transformations, but you can estimate what is the locus, the dimension, the codimension of the locus. And that is important for applications, okay? So this is, I wanted to, now I want just to say one phrase about this situation where there is no upper bound in the parameter, because there, again, there are some critical values and there are changes and so on. And even though there is no upper bound, here what happens is that as you make alpha larger, the moduli spaces stabilizes. So there is a last value where there are changes, and then the moduli space remains unchanged. So it is, again, even in that situation, there is a finite number of moduli spaces to study, okay? Now, why am I telling you all this? I guess I don't have much time to, well, I find this moduli spaces interesting things. These are interesting spaces to quantize, as you have done that. And I mean, the moduli space in these cases have universal, there's a universal moduli space like the universal divisor, and it's interesting, but that was not my motivation. My motivation came from dimensional reduction somehow, but it came mostly from something else. And but I'm going ahead of myself. But let me just, before I go to that, tell you, I had forgotten, I had this session. And so the thing is that you can, now this is a machine, right? That you can perform. And now why do we restrict to SU2 equivariant holomorphic vector bundles on X cross P1 like the ones that I said before? Why don't we classify them all? And so the classification is that in fact, all of them are classified by what we call chains. There is a one-to-one correspondence between SU2 equivalent holomorphic vector bundles on X cross P1 and chains like this. And so we can absolutely study these things as well. There are vortex equations and so on. And I want to explain what is my motivation to study these things, but we will have to wait until tomorrow. But before that, I want to tell you that in this case, the stability involves as many parameters as actually as many real parameters as morphisms we have here, right? And now I am coming to the question that you were more asking, you know, and okay, well, you see P1 as we put here, P1 is really this homogeneous space of SL2C, but why not considering another complex reductive group, G, and a parabolic subgroup? And, you know, the study of homogeneous bundles, this is a Flach variety, generalized Flach variety. The study of homogeneous bundles on Flach varieties is one of the wonderful subjects that relates to representation theory of the groups and many things in algebraic geometry. And we want to go beyond that by considering the product with X, right? And now with Luis Alvarez Consul, we investigated this more general situation of equivariant G equivariant bundles on this and the dimensional reduction procedure. And we found out that actually in this situation, there is a quiver that is determined by P, right? And this quiver, actually the vertices are determined by irreducible representations of the Levy subgroup, of a Levy subgroup, and the arrows are determined by the unipotent part of P, and is a quiver with relations, right? a bit more complicated. So for the case of, for this P here, the quiver is this, it's a linear quiver, right? But in general, there's a quiver with relations. And again, in this situation, we were able to apply all this machinery. But in any case, even if you have a quiver that doesn't come from this kind of setup, with Luis also, we prove a general theorem for quiver bundles, meaning a representation in the category of quivers in the category of vector bundles of a quiver, right? And so, but these ones did appear very naturally from this kind of dimensional reduction. And so this was again bringing to algebraic geometry this machinery that is so familiar to physicists and differential geometers of dimensional reduction, right? To obtain, to give some kind of interpretation to these moduli spaces. So I am over time, but I won't say anything, but to say my motivation to study these things didn't really come from, well, dimensional reduction was one generating thing, but it came mostly from the theory of Higgs bundles. And in fact, the first paper by Hitching, where he considers rank 2 Higgs bundles, and he analyzes, he wants to study the topology of this moduli space and see that inside the moduli space of Higgs bundles, there are abelian vortices. And so vortices are, I don't know what's the word in English, there's people that like to live in other people's homes, right? And, they like to live in, in the moduli space of instantons, and they like to live in the moduli space of Higgs bundles, right? And so, but in the moduli space of Higgs bundles, I mean, in the case of instantons, they give examples of solutions. In the case of the moduli space of Higgs bundles, they have a function that is very important, which is they control the topology of the moduli space of Higgs bundles. And so that makes them very powerful. So I'll stop here. Yeah.
Thank you, Oscar. Okay, so are there any questions for Oscar?
Touching a point, huh? Nuno knows. Actually, as I said, the vortex equations make sense on the original, even a billion vortex equations make sense on higher dimensional Kähler manifolds, right? In particular, they make sense on Kähler surfaces, yes? And it so happens that these Seiberg-Witten equations, when you consider them on a Kähler surface, they are the vortex equations. So they have a more important status. They are the vortex, they are the solutions to the Seiberg equations. Yeah. The thing is that, of course, the Seiberg-Witten equations do have a life above from Kähler geometry in any four-dimensional Riemannian manifold, and for which you need spinners, right? And in case of a Kähler surface, spinners are very simply described in terms of holomorphic sections, line bundles. This is why they are exactly the vortex equations. And the existence theorem of solutions to the vortex equations. Oh, I should have added that there are many proofs of the existence theorem for the vortex equations, and Witten gave another one. We have to tell him there was, when he introduced the Seiberg-Witten equations, that this theorem had been already proved years ago. Yes.
So any more questions for Oscar? So let's thank him again.